All right, next in the unit, we're going to look at transformations and characteristics of rational functions. Specifically, we're going to be looking at simple rational functions, so y equals 1 over x or 1 over x squared. So for y equals 1 over x, I'm just going to make a table of values so that I can sketch a graph for it. So I'm going to be using -2, -1, 0, 1, and 2. So if I plug in -2, I get -1/2. If I plug in -1, I get 1 over -1, which is -1. If I plug in 0, I get 1 divided by 0, which is undefined. If I plug in 1, I get 1 divided by 1, which is 1. And if I plug in 2, I get 1 divided by 2, which is 1/2. So what I end up with is -2, -1/2, -1, -1, and then 0 is undefined, so that's a vertical asymptote. And then I get 1, 1, 2 is 1/2. And so you actually get curves that end up looking like this. And what actually happens, if you can imagine plugging in +3, plugging in +4, plugging in +5, the higher the number for x, the closer you get to the y-axis, or sorry, to the x-axis without touching it. We actually have a horizontal asymptote as well. So we have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. I'll go ahead and do the same for the other simple rational function, y equals 1 over x squared, so I'm going to use the same table values that we're used to using, so -2, -1, 0, 1, and 2. So for -2, I have 1 divided by -2 squared, which is 1/4. 1 divided by -1 squared, which is 1 over +1, so that's 1. 1 divided by 0 squared is undefined, so we're going to have another vertical asymptote at 0. 1 divided by 1 squared is 1. 1 divided by 2 squared is 1/4. So -2, 1/4, -1, 1. We've got that vertical asymptote. 1, 1, and 2, 1/4. And so here, this is what we end up getting. And if you can imagine plugging in 3 on the bottom, 3 squared, 4 squared, 5 squared, the same thing happens as with 1 over x. As we get further along, as the x get bigger and bigger, we would get closer and closer to the x-axis, so we have a horizontal asymptote for this rational function as well at 0. So vertical asymptote, x equals 0, horizontal asymptote, y equals 0. So for this parent function, for both of these, we don't really talk about a locator point, we don't really talk about a vertex, we talk about the intersection of the two asymptotes. And I'll talk more about the asymptotes in a second. All right, so here are the two parent functions with the transformations written in. So we have a as the coefficient, I've written it in the front, x minus h or x minus h squared with a plus k on the end. So you know that if it just has x minus h, that the two curves are on opposite corners of each other. If there is an x minus h squared, then the two curves are on the same side of the x-axis, they're both above. If you have a reflection, then instead of being top right and lower left, then they would switch. This one would reflect up here, this one would reflect down here. For this graph, if there's a reflection, they would both go down here. So we can go ahead and write the transformations are the same as they've always been. So if A is negative, then that's going to be a reflection over X. If the absolute value of A is greater than 1, then that's a vertical stretch. If the absolute value of A is less than 1, that's a vertical compression. Positive for H means it moved to the right. Negative for H means I almost wrote those backwards. The H is the opposite of what you would think. So positive means it moved to the left. Negative means it moved to the right. For K, positive means it moved up. Negative means it moved down. So exactly what we're always used to. All right, so before I go much further, I just want to read down here. An asymptote is an imaginary line such that the distance between the curve and the line approaches 0. So the distance between the curve and the line gets smaller and smaller and smaller. Teachers back in the day might have said that the curve got closer to the line but never crossed it. And while this is often the case, it is not always true, and it is not the definition of an asymptote. It's actually wrong. It's just easier when you're younger and first learning about asymptotes. It's easier to describe them that way for students who are less mature. And I don't mean like you're silly, like you. I mean less mature, like you're younger and your brains are not as fully formed and can't handle more advanced mathematical concepts. So now that you're in Honors Math 3, now that you have gotten to the point where you have taken math a little bit longer and you can handle things that are a little bit more complicated, now we get to the point where we say, well, asymptotes can actually be crossed. They just aren't crossed all the time. So you'll see actually in pre-calculus, honors pre-calc is where you start to see asymptotes get crossed. But the real definition of an asymptote is a line where the distance between the curve and the line approaches 0. So an asymptote is an imaginary line where the curve is just getting a lot, it's getting closer to it. As time continues, basically. And then as you continue to study mathematics, you will see that asymptotes do in fact get crossed, and it happens more often than you might think, right? But in the functions, when we deal with these functions, those asymptotes will not get crossed. It's only in the more complicated rational functions that they get crossed, and you will not be seeing those in Math 3. You'll be seeing those in pre-calc. All right, rational functions do not have a vertex or locator point, but they do have two asymptotes. They have a vertical and a horizontal one. The intersection of the two is the HK that we're used to. So that's where the 0, 0 is the intersection of that vertical and horizontal asymptote, the intersection. So the vertical asymptote is x equals h. The horizontal asymptote is y equals k. I would circle that or highlight that with a marker. Or a highlighter or whatever, that's going to be important, okay? So let's go ahead and do example 1. It says to find the transformations for this problem. So I'm going to rewrite this so that I can see my a value really clearly. I'm going to pull that -3 out and then write it as -3 times 1 over x plus 1, and then a plus 1 on the end, so we can really see what's happening there. So with that -3 in the front, 1 on top is normal, 3 on top is not. So that -3 tells us that we have a reflection over x, and we also have a vertical stretch. So this graph is taller than normal, taller, skinnier than normal. Then down here I can see that the graph has shifted to the left 1, and it has shifted up 1. I wrote S for shift, but I don't need to write that. It has shifted up 1, right? Now, the H and the K values are also going to tell me the asymptotes, and that's going to be something that's pretty common for us to find because it's very important. So my vertical asymptote is at x equals -1. Do not ever tell me vertical asymptote -1. It is the equation of a vertical line. So vertical asymptote is x equals -1. You can see that right here, x equals -1. My horizontal asymptote is the equation y equals +1 for that number on the end. So it's the same as the way that we've always found h and k. It's the opposite of the inside of the function. This time the inside of the function is the bottom of the fraction, it's the denominator. So it's the opposite of the inside of the function and then the end of the equation. Right? So we've got our transformations, we've got the vertical and horizontal asymptote. All right, so let's go ahead and find the domain and the range next. Example 2, so to find those, finding the vertical asymptote and the horizontal asymptote are going to be important. You'll see why in a minute. So the vertical asymptote is, for this graph, is going to be x equals -5, so it's the opposite of that number. The horizontal asymptote is going to be y equals -3. Now these numbers are important because those asymptotes are lines that cannot be crossed, which means they are basically excluded values. So that vertical asymptote of -5 is an excluded value of x. So for the domain, I'm going to say that x is all real numbers, except x cannot equal -5, so this is the set notation. And the way that I would write that in interval notation is I would say I have all the numbers from -∞ all the way up to -5, but I'm not going to put a bracket around -5 because I'm not including it. So for this part, -∞ up to -5 with a parenthesis around -5. So that's the left part of the graph. The right part of the graph starts at -5 and then goes all the way to +∞. So I've got a U, -5 to +∞. Now my excluded value for the range is -3. I'm going to say for the range, y can be all real numbers, but y cannot be -3. So I'm going to do the bottom half of the graph and the top half of the graph. For the bottom half, I've got -∞ all the way up to -3. And I'm going to put a parenthesis because it cannot include -3. So -∞ up to -3. And then the top half of my graph is from -3 up to +∞. So again, these are the set notation. And then this is the interval notation. My preference is the interval notation. I do think that the set notation, honestly, is probably a little bit more comfortable because it feels a little bit more straightforward. I'm okay with either of them as long as you just commit to it. So either put both answers in the set notation or put both answers in the interval notation. As far as what you're more likely to see on the EOC, I'm going to assume the interval notation, but both of them are valid. All right. For our increasing and decreasing interval, we're going to go ahead and draw our stick figure diagonal. So, and just like we always do, we're going to use only our x values. So we have our stick figure starting over here at a left arrow. So he is starting here at -∞. And he starts walking and he walks downhill. He's walking like down into a valley. So he is decreasing in this picture. And he decreases to this vertical asymptote, so he is decreasing into this x value of 2. And he decreases into an abyss. I don't know. He decreases into an abyss, and that is the end of that stick figure. So we have one stick figure who is decreasing from -∞ to 2. And then a new stick figure starts at 2, and he crawls out of the abyss. So he's coming up out of the abyss, up over this hill. So this guy is increasing up out of the abyss and going to this right arrow, which we know is a +∞. So we have a new stick figure who is going from 2 to +∞ up out of the abyss. So decreasing interval and increasing interval for that example problem. All right. As far as maximums and minimums, relative maximums and minimums, rational functions don't have them because we know maximums and minimums look like mountaintops or valleys. And when we look at both of the types of pictures that we have, this type of picture here, this type of picture here, neither one of those looks like a mountaintop or valley. All right, this video is getting long enough, so we're going to do x-intercepts, y-intercepts, continuity, and end behavior in class tomorrow. So do not worry about any of the notes, any of the rest of the notes. We're going to finish those in class.